Hello everyone, this is Mr. Fugay and welcome to this video. We're going to talk about linear and angular velocity. Now, whether you've had an introduction to the differences and similarities between these two or not, I'm going to provide a very quick intro using the idea of a merry-go-round. And here the idea of this is that a merry-go-round, when it moves around, can be looked at upon two ways as you as the writer. One is we have two different children over here. They're sitting on the merry-go-round. We have child one who sits on the outside and child two who's sitting on the inside. Now, as the merry-go-round moves, it moves in a uniform motion. And that uniform motion is how many degrees or radians that we want to turn it in a particular amount of time. So let's say it moves at 30 degrees per second, okay? Whether you're child one or child two, you are moving at 30 degrees per second with perspective being the center of that merry-go-round. But what is different, however, is that child one and child two are having similar experiences but different experiences. And that is that child one in that time is actually traveling a further distance around in order to complete that revolution. So a much longer trip over the same amount of time as child two, who's going around a much shorter trip. And so what that means is that while their angular velocities are the same, 30 degrees per second, their linear velocity, the actual experience they're feeling while they're moving, is actually different. Child one is moving faster than child two. And so it's really important to note those differences as we talk about linear velocity versus angular velocity. So let's talk about linear velocity or linear speed, linear velocity first. So first thing I want to point out is in terms of its units, we're going to refer to this as whatever the distance unit is per time. So examples of that would be miles per hour, very common linear speed. Note feet per second, that's another common one. Centimeters per second, and I could keep going on all day with these, but those are the most common ones. Okay. So the idea is that if P is on a point of a circle with a radius r, and P moves some type of distance, which we can calculate now that we know what arc length is, then we can find the linear velocity using the classic formula distance equals rate times time. But I'm going to move this around a little bit. I'm going to divide time on both sides. So I'm basically going to say distance divided by times is your rate. Rate is another word for velocity. And so what we want to create is essentially a formula that says your speed on the ride or whatever it is you're doing is going to be equal to your distance divided by your time. So in note, what we want to do is basically say that V equals S over T. Now, what is S and T? S, remember, is going to be the total arc length that was traveled. So let me add that word total, arc length, and that's divided by the total time traveled. Okay. So if we're trying to compute the velocities of child one versus child two, notice that we would have to compute arc length, and arc length uses a radius. So we're going to end up talking about that and how child one is moving faster than child two. So here's an example. And the last thing I'll note before I move on to that, notice that they are both circles at the end of the day. The red circle and the green circle, while they are part of the overall merry-go-round, they are circles in their own right in terms of their traveling path. So let's look at an example. It says a point on a circle travels 5 centimeters in 2 seconds. We want to find the linear velocity of the point. So we're just going to look at the formula V equals S over T. In this case, we're just directly given this information. So it's going to be 5 divided by 2, which means the answer here is going to be 2.5 centimeters per second. That's going to be our unit that we're going to use in this situation. So that's it. That's all really linear velocity is at its core. And we're obviously going to mix all this together in the video, but that's all we need to know as we move to the second part, which is a little different. It's angular speed, or angular velocity as we'll call it. So this is always going to be a unit of the angular measure per time. So an example of that could be degrees per minute. It could be radians per hour. It could be revolutions per second. So notice that for the angular measure, we have 3 ways to measure an angle: degrees, radians, or revolutions. And then, of course, we have all sorts of time elements, minutes, hours, seconds, and so on. So if point P is moving with uniform circular motion on a circle and the line sweeps out some central angle. So we want to basically figure out how quickly is that angle changing as time moves on. So we want to figure out our theta per our time, a rate of that. So what we're going to use is the Greek letter omega, which is like a cursive W. I'm just going to make like a W with like a little curl through it like that to denote that Greek letter. So omega, the angular velocity, is going to be the total central angle movement divided by time. So I'll write that down. So this is going to be the total, and we're going to typically write this as a radian. So we're going to say total radian measure. So how many radians did we rotate over our total time? And again, in its most basic form, here we are. A point on a circle rotates 3 pi over 4, so that's my theta, over the course of 3 seconds. And so to figure out our angular velocity, we're simply going to take 3 pi over 4 divided by 3. Of course, can type that in your calculator, but I also know that dividing by 3 is the same as multiplying by 1/3. Those 3 cancels, and we end up with pi over 4. The units will be radians per second. So every second, I'm moving pi over 4 radians, which, as you know, is 45 degrees. 45 degrees, pi over 2 is 90 degrees. All right, so let's look at an example that uses a little bit more of this all put together in addition to some of the other formulas we've talked about, okay? So we have a bicycle wheel with a radius of 13 inches, and it turned with an angular velocity of 3 radians per second. We want to find the total distance traveled by a point on the bicycle tire over the course of 1 minute. Okay, so let's break down what we know. They know what the radius is here. The radius of the bike wheel is 13. We also know our omega value, or our angular velocity here, is 3 radians per second. So thankfully it's already in radians, so we don't have to do any conversions. The last thing we want to look at is we want to look at the total time traveled as 60 seconds. Now the reason I'm not writing 1 minute is because I noticed right away, since that's using seconds, I want to stay in the same unit of time. So I'm going to go ahead and just immediately convert it. Now, what do they actually want us to find? They want us to find the total distance traveled. So if I'm looking at a bike wheel, all right, the total distance traveled is going to be the total amount of time the bike is touching the ground, which is, in other words, the arc length. So this is what we want to find. We want to find arc length, which we're now denoting with the variable s. So let's think about what we have in front of us. So I have a W and I have a T. I do not know the angular measure. So how many degrees, or in this case, radians, am I moving? So I'm going to use my angular velocity formula, which is the omega equals theta over t. We know our rate is 3 radians per second. We do not know our theta value, but we do know 60. And so what we can see is that this wheel is going to turn a total of 180 radians, 180 radians in total. So now what we can do is actually find our arc length. Because as a reminder, we didn't use this yet, but our arc length formula for radians is S equals R times theta. So to find that arc length, we're going to plug in our radius, which in this case is 13. We're going to plug in our theta, which is going to be 180. And when we multiply them together, we're going to get a total of, that is not right. When I multiply those two numbers, we get 2,340 inches. Now, if we want to leave that as our answer, that's great. You can certainly leave it as 2,340 inches. However, if I divide that by 12, we'll see that that's the same thing as 195 feet. So this is the total distance that this wheel has rotated. How much distance has it covered over the course of that 1 minute? Now, up to this point, you've seen a lot of formulas, all right? So let's just take a quick pause, and we're going to talk about all the formulas together in unison. And then the last part of this video will be a bunch of examples that we will go through and try. So let's just remind ourselves of a few formulas we've already learned. So the first one we know is arc length. And we talked about this in a prior lesson. The letter S is typically used for arc length so that we don't mix it up with other things. So it'll be S equals R times theta. The other one that we've learned today is to find the angular velocity, or speed, whatever you want to call it, of something. We're going to use the omega, which represents angular velocity, and that's theta over time. And then we have our linear velocity, which is the first thing we talked about in this video. So linear velocity is going to be V equals S over T, where S, of course, represents the arc length. Now there's one small variation we can take of this because there's a second formula that can be denoted from this based on what we have here so far. And that is, we know that S, in this case, which is our arc length, is the same thing as r times theta. So we can write it as r times theta. But wait a second, don't we know what theta divided by t is? Well, that's going to be my angular velocity. And this brings up our final variation of an equation today, that the linear velocity of an object, v, is going to simply just be equal to r, our radius, times our angular velocity. And so this is the last variation that I'll write underneath here, is v can equal r times w. So these four equations are going to be the essentially holy grail of what we're going to be working with throughout this lesson. And so you want to use these four formulas as you need to. And just with a little magic, I've also provided on the side here something you might want to pause the video for, and that is just a quick guide of all these variables that we've thrown out here. We have English letters, we have Greek letters, we have all these sorts of things. So just to take a moment, that S is our arc length. That is the, essentially, if you're thinking about the merry-go-round, okay, that's how far you have traveled on the merry-go-round. Whereas the radius is, well, how far are you from the center of the merry-go-round? The central angle is how many degrees you have rotated around the fixed center of that merry-go-round. And then the last two today, of course, angular velocity is the speed at which the angle is changing on the merry-go-round, which, by the way, no matter where you sit on that merry-go-round, it will be the same angular velocity for every single person. However, the linear velocity is the total amount that you've traveled divided by time. Therefore, the further you are away from the center of the merry-go-round, the faster you will move versus if you're standing towards the center, and that is our linear velocity. So that is a general description of all the variables and all the equations. This page is going to be super helpful as we now move to these last few examples. And so here we go. We're going to go through a few of these together. So for the first one, it says, if a point is moving with a uniform circular motion on a circle radius r, then the linear velocity, we're going to just go ahead and just summarize what we mentioned here. This is just telling us the relationship between linear and angular velocity. But the first example that I am going to have you pause and try is this here, okay? A phonograph, which is a circular recorder, okay, is turning at 45 revolutions per minute. If the distance from the center of the record to a point on the edge is 3 inches, find the angular velocity and also the linear velocity. So try this example on your own, press pause, try it out, and then if not, we'll come back and we're going to talk about it right away. So what I see in this problem is that they gave me two important numbers. They told me that the angular velocity is 45 revolutions per minute, and what I want to also do is convert that. So remember that 45 revolutions per minute, if I want to convert that into radians, which is what we're probably going to need to do here, 1 revolution is 2 pi radians. So I know that the angular velocity can be written as 90 pi radians per minute. So I'm going to use that as my S value instead. And the radius here is 3 inches. So remember what we just mentioned here. So we've actually already figured out our angular velocity, as angular velocity should always be written in terms of radians. So there is my angular velocity done. And now that we know now that we know W and now that we know R, remember our new formula here, because the angular velocity times the radius will always equal our linear velocity based on that new formula we created. So we take our radius, we'll multiply it by 90 pi, and our linear velocity is going to be 270 pi, and in this case, we're using inches per minute. So this is that linear velocity that we're looking for in this example. So the remaining examples in this video, or in this lesson, I should say, there are, I believe, 3 additional examples. We will try those out, and I will have an additional video where we will go over all 3 of them as well. Besides that, I hope this video was helpful, and thank you for watching.